Um, so I'll get right to it. Everybody has experience with variation in software artifacts. And as soon as you see these documents and have to work with them, you have to also think about how to process them, how to transform them, and so on and so forth. And this is most prominent in analysis and all kinds of programs you want to write for software product lines, where the objective is to define programs that are variable and that can be configured to run on different systems, to have different feature sets, and so on and so forth. But there's all kinds of other applications for the use of variation in programming, for variational programming. And so the question arises how to best represent and then manipulate variational data, and in particular variational programs. And so what I want to do in this talk is I first have to give you some background and motivate variational programming, because it's something fairly new. And basically the question behind this is how to write programs that can manipulate variational data. And then I want to show you part of a formalization of this idea through a variational programming calculus. I will show you some of the syntax and a little bit of operational semantics. I probably won't have time to talk about the type system. This is all based on work we started a long time ago on the choice calculus, which is about representing variation in software. And I'll have to give you some background on that as well. Okay, so let's start by looking at a very simple variational program. Here's a program that has one parameter and a function f, and f is applied to one of two values, either 1 or true. And this choice, this variation point, is expressed by a named choice. And the name is also called a dimension for reasons that will become clear soon. And it has two code alternatives. And so what can we do with this? Well, first of all, this program, you can think of this as being written in lambda calculus, extended by named choices and operations to manipulate named choices. Okay? So what can we do with this? Well, first of all, we can make selections. We can project onto different code alternatives. So we could select the left alternative in A. These kind of things are called selectors, and then we get the function lambda f applied to 1. Or we can select the right code alternative, and then we get lambda f applied to true. And these programs are called variants, and they are just plain lambda calculus programs if all the variability in the variational program has been removed. Okay, so, well, in general, programs will, of course, contain more than one choice has many different places, and then the question arises what happens when we have choices that are in the same dimension, that have the same dimension name, or if they have different names. So here's an example for the first case. Suppose we apply this program f to a choice between the function successor and not. So we arrive at this expression, and you can see that these two dimensions are the same and they are synchronized. That is, if we make a selection to the left or the right part, well, we only have two selections to make, and the left selection in this A will also trigger the left selection in this A, and we get the program successor applied to 1, and for the right selection we get not applied to true. Now, if in contrast we use a different dimension for the function, then we obtain this expression where we have two different dimensions that are independent of one another, and that means now we have to make selections in both in A and B to produce a plain lambda calculus program. And you can see that this results in 4 possible programs. And you can also see that 2 of them are type correct and 2 of them are not. Okay? And so this also kind of explains the name dimension here. You can see when you have different names, then with each dimension, you multiply the number of possible variants. And it's kind of like a multidimensional space that is created with each new dimension name that we use in a variational program. And so, yeah, I'm using here, and in the paper and in the calculus, we're using only binary choices, but that is not really an important restriction. So, now, one of the most important aspects when we transform and work with variational programs is what we call variation preserving computation. That is, you do something to the program, and what results has the same variability as the original program. So one obvious example is you want to evaluate a program. So if you evaluate this variational program, well, the result is, again, a choice, a variational value, if you wish, between true and false, right? Depending on whether we chose the left or the right alternative. But we can do other things, right? Evaluation is only one example. We can also do type checking, and if we infer the type of this variational program, we again get a variational type, and the type is here either int or bool depending on the variant selected. Now for this program, the same thing. We can try to evaluate it, and we get a variational value back. And here you can see that we have two cases where the value is undefined because of the type errors involved. And similarly, if we do type inference, we also get, in this case, a variational type, and we have two type errors that are also reported here as part of the variation. Now, this tabular representation here of what these variational programs represent illustrates or indicates already an approach how to do variation preserving computation. You could basically think of an approach which performs all the selection. You get all of these plain programs, and then whatever you want to do with the variational program, you do to each individual variant, okay? And then this gives you basically all the possible values. Now, this approach is theoretically possible, but it's rather infeasible and doesn't work very well in practice. So if you think of a bigger variational software package where you have lots of dimensions, and you want to generate all the program variants and then analyze them or evaluate them one by one, well, that can take a long time. If you just look at MySQL, which has 250 features, I think, well, that leads to more variants than there are atoms in the universe to the fourth power. So that would take a long time to compute and is clearly not feasible. So instead, what we want to do in variational programming is work with the variational values directly. And that is one of the critical aspects, I think, that we think is important when you think about variational programming. So you have this variational program, and a variational computation produces a variational result. And it's important, I think, for any system that is hoping to be efficient and feasible in practice, that it can manipulate variational values directly. And the other approach of performing selections repeatedly, then breaking down this and performing computations on individual results, that, yeah, it's kind of a simulated variational computing, but that won't scale very much. Okay, so one very important aspect of variation preserving programming is captured in this law, which says that if you have a choice that sits somewhere in an expression context, well, you can push this context into both alternatives of the choice. Or alternatively, if you have a choice with two code alternatives that have a common context, you can pull this context out, okay? And we can see how this applies in evaluating, for example, our second example here. If we look at this expression, we can use this law to first push the function here, the variational function, into both of alternatives of the argument. And then in the next step, we can, in each alternative, push the argument into the alternatives of the variational function. And now you can see here in the result here, we have these four cases, which really corresponds to the four cases in this table that I've shown earlier. So this law, this choice distribution law, is essentially capturing this idea of variation preserving computation. And since this is such a predominant idiom in programming with variations, this is kind of built into the language. So by default, computation behaves like this. Now, variation preserving computations is only one example of variational programming or variational transformations, and variation elimination is another one. And this is just an example of the more general aspect or the more general idea of variation aggregation. So elimination can be simply done by a function cell that, well, takes a selector as an argument and a variational program, and, well, it performs the selection. And you can see here, if you have multiple dimensions in your program, you need multiple selections in order to get rid of all the variation to get a plain program. And, well, the order of selections doesn't really matter. And also, it should be obvious that you need as many selectors and selections as you have independent dimensions in your variational program. Okay. So now, more generally, what we want to do is eliminate, when we want to do elimination of variation. We want to do this in a systematic way. We want to aggregate a variational value into a plain value in a systematic way. And as an example, let's consider the task of computing the minimum of a variational integer. Okay? So we can envision writing the following function. Call it vmin for variational minimum. And you can see here this construct any attempts to detect and find a dimension in this variational integer. It might or might not contain a dimension. If it does, well, it will select the left and the right part of that in that particular dimension and apply the variational minimum function recursively to it. So the result will be two integers, and we can simply compute the minimum of the two to get our result. Otherwise, if any is unsuccessful, if the argument does not have any variation in it, well, this is just a plain integer and it's minimum already. Okay, so this looks okay. So we can try to apply this vmin function to our variational value, right? And so what is the result? What do we get? Well, we do not get 2. Surprise, surprise, we get the original value back. Well, why is that? Well, this is because of this principle of choice distribution that I mentioned before, which is built into the language. So vmin, without doing anything else, vmin will be simply distributed to all the alternatives and compute the identity for each plain number. So that doesn't work. So we have to do something in order to make it work, because this is such a nice function here. We want to make it work. And what we need in order to make this happen is this annotation for parameters to block this choice distribution, right? So if we define a function that has this annotation on a parameter, well, this will prevent choice distribution from applying, and aggregation and the variational value is preserved, and then aggregation can work on this variational value. So with this definition, we get the value that we intend. And since this pattern here of extracting a dimension from a potentially variational value and then performing computations recursively on both parts, on both alternatives, well, that occurs very frequently, and so we've introduced several derived forms to make this look a little bit better. So here's the split operation, which, well, tries to find a dimension, and this any keyword indicates, well, we don't care what it is. And then here, it offers us the name, it binds the name of the found dimension to D, but it also binds both alternatives to the variables L and R, and then we can use this here in the recursive computation, make it a little bit smaller. Okay, so as one example application, I want to show how we can implement a function for doing variational unification. Now, variational unification is the question of you have two variational types, and you want to make them equal. Okay. So it's a generalization of traditional unification, but, well, with variational types. And so this has actually quite a few applications. We've been using this very successfully in many different areas. And it's also not obvious how to do this. It's not trivial. So if you look at this particular case, well, one obvious substitution is this one. We substitute each type variable by int. And then if you look at all possible selections here, it doesn't really matter what you select. Well, the result will always be int. And so this substitution makes these two types equal, right? Independent of what selection will be made. Okay, but this is not the only one. There's actually quite a few other substitutions that also make this equal. And the reason for that is the number of different laws that govern choices. And so we have seen one already, the choice distribution, but there's also idempotency and choice domination. So it's not obvious to come up with this unifier for this case. And this is how these unifiers are related to one another. So how can we implement variational unification? Well, in a language based on this calculus, we first have to define a type for types. Right? This is what we want to work with. Now, what we can observe here is what we don't see, namely the absence of a constructor for representing variation, because this is built into the language. Right? So we don't even have to mention this anymore. And then our variational unification algorithm looks as follows. Here we mark the two parameter types as blocking, non-choice distribution preserving, so that we can aggregate the variability in it. And so what we do first is we try to find variability in T in the first argument type. And if we find that, well, then we try to split U, the second type, on the very same dimension. So here's a separate, this is another split command. This looks very similar to the first one here, but it splits on a specific dimension. And if we're successful, well, then we can unify recursively both parts, the left and the right parts of T and U. Otherwise, if U does not contain D, well, then we have to unify the left and the right part with U as a whole. If T doesn't contain any variation, well, then U might still contain variation, and we get a mirror case of the second case. And finally, if there's no variation either type, well, we can simply defer to a traditional unification algorithm. So the nice thing about this is that it's rather short, and more importantly, that the variational computation is clearly separated from the non-variational one. So this supports the modular writing of variational programs. Okay, so let me briefly talk about the calculus itself. So we have a whole bunch of different namespaces for expression, dimension variables, and dimension names. And then in the calculus, we have traditional lambda calculus. We have constructs for building choices and performing selections. We have these two operations for querying variability. And then most interestingly maybe is the abstraction here, which first of all allows us to abstract not only over expressions, but also over dimensions. So we can really compute with variability. And then we have this annotation here, which allows us to block choice distribution for parameters if we so desire. The values are defined in an obvious way, but choices are also values, and dimensions also. So the operational semantics, well, we need to address all these different cases for variation computation in addition to ordinary lambda calculus. So there is variation elimination, which works really in an obvious way. We can select the left and the right part of a choice and have to do so recursively for the selected alternative because there could be nested choices in those parts. And for variation preservation, we have to now realize this choice distribution principle. And the first case is if the function to be applied is a choice itself, well, then we move the argument into both code alternatives. And again, we have to make sure that we select with a dimension in the left and right alternative for the argument. The reason for this is related to choice domination, which I haven't shown, so I will not explain this here. The other case looks more complicated than it should at first, because we might have expected that we can do pattern matching on the argument on a choice, but this doesn't work because the choices can be nested deep down in E prime. And so what we have to do is we have to reduce this to an application of the split form, where we extract the dimension, the variability, and bring it to the top level, and then perform a reduction in the arguments. Otherwise, if there's no variation, then this is just plain beta reduction. And the same is true for the blocking version of application. There is also these 4 rules for variation aggregation. So if we want to query an expression for dimension, and then depending on whether or not we find it, perform E or E prime, well, this depends on the variability in the argument. And we can know 2 things here. The first thing is that the argument here must be a value. And the second thing is that, well, we have to have this auxiliary function dims for computing the dimensions that are contained in there. So this is not really nice, but it is something we had to do in order to make this whole thing work. And for the results look, or the rules look very similar. I will skip over the type system because I'm kind of running out of time. The only thing I want to mention here is that the type system works in 3 steps, or in 3 layers. First, there's this base layer for ordinary lambda calculus types. Then we extend it by variational types. And then here for type schemas, you can see that not only do we have polymorphism for expressions, but we also have dimension polymorphism. So we can really abstract over dimensions, and that can also be bounded. And these bounds result from dimensions that are extracted, as you can see here, from expressions. And much of the type system is actually concerned with deriving these constraints and then solving these constraints. It's kind of a limited form of dependent type system that makes this so complicated. So, to conclude, variation is found in many software artifacts, and so we have to find a way, if we want to work with software artifacts, to transform variable or variation containing software artifacts. And this variation programming calculus is one proposal to do that. I wanted to give you the happy end sign here, but we're not there yet. There's actually a lot of open questions, and moreover, there are certain design decisions that are in this current calculus that we're not fully happy with, but that we had to do in order to get certain theoretical results like type preservation and so on and so forth. So there's many more questions to be considered, and I think I'll stop here, and I'm happy to take your questions.
Thanks. That was quite interesting.
Thank you.
Quick question about the one of the earlier slides, and this might have just been like a typo, but in one case, when you had a sort of nested variation,
right.
The example came out sort of like it was B followed by an A.
Mm-hmm.
And in a later slide, it looked like a very similar example, but it was an A with a B nested inside of it. And so I guess what that got me wondering is if the slides were simply like maybe there was some difference between the two examples that I didn't notice, or if there's actually some sort of non-determinism in how this reduction works.
Right. Okay, so the nesting of the choices can always be reverted. If you apply this choice distribution backwards and forward, you can actually exchange the nesting of the choices. This doesn't really matter. And as far as non-determinism is concerned, since we have I've mentioned this function dims when you do variation aggregation. When you select an arbitrary dimension, this is based on the particular ordering of the dimensions. So this also preserves deterministic computation. But the nesting, let's see, this was on the next slide, I think, maybe. No, it's even further. I think this one is what you're referring to, right? So here A is out on the outside and B is on the inside. If you do this the other way around, you can first move the B choice into the A choice, and then you get kind of the flipped version of this table. And they are equivalent. And the criterion is the semantics. The semantics is really a mapping from these selectors, or sets of selectors, to plain programs. And that is the same. Thanks.
Yeah, have you looked into this functionality? Like, maybe there's a monad or some encoding.
Yeah. So, well, we have a prototype implementation of some parts of the calculus, but not the full language. A monad itself probably won't do because. Yeah, we have some tiny little prototypes, but nothing we have made official so far. And one reason is, that's the last slide, we're still not really happy with some of the design decisions that we were forced to make. There's one over there.
Is it possible that sometimes you discover that a variation choice doesn't matter because you get the same result either way? Is there an operation in the calculus for eliminating choices in that case?
Yes, so there's this choice idempotency law, and so if you have a choice between two equal values, well, it doesn't really matter. So you can still write programs that have these kind of false choices, if you wish, and you will get then duplicated results. So there's no automatic way of eliminating them. At least we haven't done that. You could, of course, write a program that tries to, if you have an equality function, that transforms the program to eliminate those cases. That you could do. You might discover that only during reduction. Yes, that's true.